All right, so here is, so yeah, this is all from missing stuff. So what I'm going to do here in this video is that I'm going to show you how to translate a position time graph, so data from a position versus time graph, into a velocity versus time graph. Then we're going to look at the position versus time graph of a motion, an object that's undergoing accelerated motion. We're going to then be able to translate that graph into a velocity versus time graph, and then determine the acceleration of an object using a velocity versus time graph, as well as its displacement. Okay, so that's what we're going to do, and let's do it. So the first thing I got here, this is a position versus time graph, and it shows the position versus time of a runner. This looks a lot like the Mr. Gartner graph that we did, but yeah, we're going to translate this from a position time graph. We're going to use that exact same data and turn it into a velocity versus time graph, which is what I got here. So this is velocity versus time. Here's my origin, my 0. Here's positive velocities. Here's negative velocities right there. So that's what this is right here. And then lastly, I got these dotted lines to identify distinct points where the velocity is abruptly changing. We're being a bit unrealistic here and saying, oh, the velocity is going to boom, suddenly shift really quickly into another velocity. And let's see. So let's see. How would I get velocity from a position time graph? Well, if you remember, velocity is the slope of a position versus time graph. So, in order to translate this, let's start with A. Right? Okay, I'm going to look at this. I'm trying to get the velocity, right? So, at A, oh, I can look already. Is that slope constant? Yeah, the slope is constant, so it's going to be at one value. The slope is going to be at one value from 0 to, it looks like, almost 10 seconds, right? So, okay, what is the value of that slope? Well, let's see. I could calculate it. I'm just going to do qualitative here for time's sake. But I want to say, okay, let's see. I'm just going to say that it's, so it's constant. So if the value is constant through that point, and it's positive, right? This slope is a positive slope. So it's going to be a positive slope, but constant. And so it might look something like that. So there you go. There's my first part at part A. So this was part A. All right. Now I'm going to look at part B. Once again, the velocity is the slope of the position versus time graph. And what is this slope? The slope of part B is 0. Slope of a horizontal line is 0. So I translate that part. So there's that. There's part B. That's the velocity. And the velocity is constantly 0 until it reaches this mark right here. And next up, the last one I'm going to do is part C. Part C, I can go, oop, that's a negative value, so it's going to be a negative slope. That's going to be below my 0 mark then for velocity. However, which slope is steeper? Which slope is steeper? Is C steeper or is A steeper? Hopefully you can see that C is steeper. Again, if you want to calculate it out like you're going to do in that graphic motion kinematic worksheet, you can totally do it. But I'm just going to write it out right here. And so it's a little bit steeper, so the value is going to be steeper, but it's still constant. The velocity is still constant. The slope is still, it kind of stops right here, right? So there we go. Maybe something like that. And there you go. That'd be part C. And there's my translation of my velocity versus, my position versus time graph into a velocity versus time graph. So you should be able to do that homework question now. All right, moving right along. Let's move on to this acceleration lab. Let's hope it's here. Yep, there we go. So, so you guys did your acceleration lab. You graphed position versus time data of the thing that was traveling down, right? So I'm pointing this out, and so the reason I want to do all this is because I was very particular in like where you place that measure marker and where you where you did all of that. So because I want to let's see if I can really quickly here. Sorry, I should have had this ahead of time. But you had this ramp. The ramp went down like this. But then you started your measurements maybe like right here where the puck already went down a little bit. The puck already went down a little bit. And you started your measurements. This was 0 right here. And then you had all this. And then it went up to about 120 centimeters at t equals 0.6 seconds, where when t equals 0 seconds, the puck was basically right about there. So it was already moving, but it was right there at the 0 position. I did that on purpose. I wanted you to do that on purpose. And so first off, you can see here, right, you got a position time graph. Some people were trying to make it a linear graph, but it's definitely making more of a curve shape here. It's kind of making this curve shape. So what we're going to do is we're going to say, okay, it's modeling a curve. We'll say it's modeling a quadratic function. And so that's what this is made here. But you can see, right, this puck was accelerating. It was accelerating. So you often think, like, oh, if I got an object and right, isn't it kind of weird that I just have an object and I drop it? I have an object, it's at rest, and all of a sudden, it starts moving, right? It doesn't happen in this direction. It's not like if I let this go, it goes like that, right? So if I let this go, it all of a sudden starts moving. That's kind of weird, right? But that's an acceleration. That's what we mean by acceleration, that at first the velocity was nothing, and then it turned into something. So it started to speed up in some way. And that's exactly what we're seeing here in this graph, is that the slope is not constant like the graph that we just did just before. The slope isn't constant. It's actually constantly changing. It's constantly changing. In fact, if I were to make a tangent line, so if this is a line here, chopstick, yep, and this is a vacuum filter. If I had a tangent line, that means that it just touches the curve, but doesn't, it doesn't touch through 2 points. It doesn't do something like this. It just touches the curve on the edge, and so you see that line creates a slope that was like, if we were at that point, that's kind of the slope that point would generate there, like that. This is what I mean by tangent line to the curve. More on that on Friday. More on that on Friday, because that's going to get into derivatives and stuff. So I can do similar things with a ruler here. You can see that the slope at the beginning it's something, it's a value, but it's small compared to, as I keep moving here, the slope keeps getting steeper and steeper and steeper and steeper. So as time is going on, remember, the slope of a position time graph is the velocity. As time is going on, the velocity is increasing. It's getting bigger. All right, it's getting bigger. And if you go to that, if you go on that link that I sent you, or it's actually embedded in the lab itself as well to that video, that YouTube video, the guy describes very well on how to find those tangent lines and to graph a velocity versus time graph. And that's what I'm going to go to next. So if you see any kind of curvature happening on a position time graph, you can assume that that graph is accelerating. So when I see this curve, I go, oh, this object's accelerating, because only things that have straight lines have zero acceleration on a position time graph. So anyway, you translate that to a velocity time graph. This is data that I got, I forget who I got this from now. This is data that I stole from somebody, though. This is their velocity versus time graph. Velocity is in centimeters. We typically will use velocities in meters and time in seconds, but in this case with this lab, things are going so fast, we're going to keep it centimeters. They had their y-intercept. Their y-intercept was at 94 centimeters per second. So if you didn't answer it already, what is the y-intercept of this graph? What is that representing? Well, that'd be representing the velocity. It'd be the velocity when your time is equal to 0, right? So it's the initial velocity of when you started collecting data. Now, even though the puck was dropped at rest, back up here, but you didn't start collecting data until some time later on, where it actually gained some speed already. That's why you're getting that 94 centimeters per second, or whatever you got, depending on how you set that up. So yeah, it's the initial velocity of your graph right there. Nice. Yeah. Okay. Cool. So there's that. We also got the line that they use, so I'm going to pull that out for later. And then I got all these values here. I don't think I need this right now, so I'm going to cut that right now. Okay, so what I'm going to do is I'm just going to define for you, so I'll get to this equation in just a moment, but I want to say, okay, let's say I wanted to calculate the slope of this line. This is the velocity versus time graph, and I want to, oh, you should probably see too, it's going to make a pretty linear line. It's going to make a pretty linear line. So this means the acceleration, while the object is I haven't defined acceleration yet. So it's a pretty linear line, yeah. So it's a pretty linear line, and let's say I wanted to calculate the slope. So if I wanted to calculate the slope, I would again pick 2 points. I'm going to just be general here. So this would be t1, comma, that's time 1, comma, velocity 1, and this would be t2, comma, velocity 2. And now I want to calculate the slope of that line. So the slope would be v2 minus v1 over t2 minus t1. And that slope would give me, oh, this is Monica's data. All right, so Monica, thank you. So this is Monica's data. So that slope would be, well, that's the change in velocity over the change in time. And those of you who don't know, the change in velocity over the change in line, over the change in time, is your acceleration. And it would be your average acceleration. So that's the mathematical definition of acceleration. It is the change in velocity over the change in time. So acceleration is the slope of a velocity versus time graph. Or the change in velocity over the change in time. Or sorry, the rate of change of velocity. Now, what about the units here? Let's look at the units because I want to focus on this really quickly. So let's see. So velocity is in meters per second divided by time, which is seconds. So that's going to be, let's see. I got fractions within fractions, so I got to do 1 over 1. If I'm dividing fractions by fractions, I got to multiply by the reciprocal, right? So this is going to be meters per second times 1 over seconds. So meters times 1, that's meters. And then seconds times seconds, that's seconds squared. Now, this is typically how we're going to write the units for acceleration. Physicists go, I'm just going to call it meters per second squared. But I will say a meter per second, let's go back. Let's go back to velocity again. This idea of meters per second is much more intuitive. So what this means is that the velocity is changing. Whatever your acceleration is, let's say your acceleration is 2 meters per second. What this means is that your velocity is changing 2 meters per second every second. Let's say it's you're at rest and then 2 meters per second. So if you're at rest and you're accelerating at 2 meters per second, that means that the next second that goes by, I now am traveling at 2 meters per second. So again, the acceleration in this is, just to be clear, my acceleration is 2 meters per second, and then my initial velocity is 0. So 2 meters. So if I'm at rest and I'm accelerating at 2 meters per second, then at the next moment, the next second, I'm traveling at 2 meters per second. And now if I'm accelerating at 2 meters per second, then the next second after that, I'll be traveling at 4 meters per second. And again, if I'm traveling at 2 meters per second, my acceleration, then the next second that goes by, I'll be at 6 meters per second, etc., right? So this is the idea of acceleration being meters per second. It's how much your velocity is changing every second that goes by. However, we tend not to, when we start getting a little lazy after a while, we get into fractions within fractions. It gets a little annoying writing meters per second. So instead, we just write meters per second squared, and that's what we use for units for acceleration. Okay, the last thing I wanted to point out is this equation right here. So this is again in a general y equals mx plus b format, where this y value is telling us the final velocity. The slope gives us, the slope gives us the acceleration. X is the variable time. And then B, like we said already, is the initial velocity. So yeah, so that equation is giving you all that information as well. All right, so hopefully that was clear. Okay, and then next up I want to go with this last thing. So here's the equation again. I'm just going to take it and go. So like in this I have to go to the actual graph. Is this it? Yeah. So this graph, now you guys might see your graph might look something, probably looks, not like that exactly. It might look something like this. So it might cut off at the bottom, at the bottom here. Or it might even do the opposite. It might even cut off up here too or something. You want to try and stretch it. So this shouldn't be like this. You should see your origin. So you can actually grab it at the bottom there and drag it up and down and make it bigger or smaller. So you should see it like that. If not, at least try and identify what your vertical intercept is, and you're going to create and then I'm going to go from the 0.6 meter mark. So you're going to sketch out like I've done here, a velocity versus time graph. Mark 0.6 seconds and find out what. So either figure it out by extrapolating back on that to find out that data point, how much that velocity is. But I read it off. It's about 308 centimeters per second. Again, typically in this class we're going to use meters, but this works out better with centimeters. And then the y-intercept is 94 centimeters per second. And then here obviously is 0, 0. So you're just going to make a graph. You're going to basically, you see that shape? You see that shape? You're going to calculate the area of that shape. So I'm going to take a moment and stop. And you try and do that yourself. Find the area of that shape, and try and figure out what it means, what the area of that shape that I just made there means. So I'm going to stop. Try it yourself. Pause the video. Try it yourself. Good. Hopefully you're back now. So one thing I can do definitely is just to just kind of split this up like this. I can split this up like this, and instead of knowing, I don't know the equation for a trapezoid, so I just split this up into area 1 and area 2, and then I'll add them up to find the total area, right? Area 1 is the area of a triangle, so it's 1/2 base times height, and then area 2 is just base times height, right here. So area 2, let's see, area 2 seems like it's going to be easier. Area 2 has a base of 6 seconds, or 0.6 seconds, so 0.6 seconds. That's the base there. The height goes up to 94 centimeters, right? The height goes up to 94 centimeters, so 94 centimeters per second. And then for this, we got 1/2. The base again for this triangle is 0.6 seconds. So 0.6 seconds is again the base. And then, but the height, careful, the height is not 308. The height is not 308, right? The height is this. This is the height. So it's 308, and then I got to take out that chunk of 94, right? So it's 308 minus 94. And that's in centimeters per second. All right. So then I get, out of all this, boom, 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 boom. First off, the seconds cancel with seconds here. Seconds cancel with seconds here. And then you can calculate all this on your own. I'll say when you add all this up, you're going to get about 120 centimeters. Centimeters. I took an area and it wasn't centimeters squared? Yes, exactly. That's because the horizontal dimension is in seconds and the vertical dimension is in centimeters per second. So when you take the area and multiply those two dimensions, the seconds cancel out and you get just centimeters left over. So what did you do where that you got, what did you do in the lab where you got about 120 centimeters? Hopefully it was emphasized and driven into you, because this is the displacement of the puck. Which I think is really cool. So once again, look at all this information that you can get from just a graph, right? This is a velocity versus time graph. The slope of it will tell us the acceleration. The y-intercept will tell us the initial velocity. And the area under the graph of a velocity versus time graph gives you the displacement of the object. So let's again write that down really quickly. So the area under the graph of a velocity versus time graph is the displacement of an object. So that's kind of the big ideas right there. The area under the graph of a velocity versus time graph will give you the displacement of that object. And the slope of a velocity versus time graph gives you the acceleration of that object. And that's a big thing we're going to do in physics throughout this whole year, especially AP Physics C, is we're going to get data, collect that data, find the slopes of graphs, and find the areas under that graphs. Those graphs. Yeah. So the last thing I'm going to do now is I'm just going to go over what I think you could do tonight and tomorrow. So here we go. All right. So everything that's in italics is something that's new. So watch this video. That's hopefully you're doing that, right? This is all Wednesday. This is all Wednesday I'm looking at. Sorry. And then finish homework 3B. It shouldn't be too bad for you. So by 11:59 tonight on Wednesday. Thursday, if you haven't watched this video yet, watch this video. And then complete graphing motion kinematic worksheet, pages 1 through 3. You could start on page 4 if you'd like. I personally think it's kind of tough. I would do the name that motion before I did page 4 of that thing. But what's nice about the graphing motion kinematic worksheet is it's very computational, lots of numbers and things like that. So, in my opinion, qualitatively translating graphs is a little more challenging. You have to have an intuition for it. It's a little more challenging than doing it computationally. So, this worksheet, the graphing motion kinematic worksheet, walks you through mathematically how to do it. And then name that motion is, it says in the thing, you got description of motion and numbered graphs, and you are to match the description with those numbers. And you're basically going to, you can then, once you've got the graph numbers and the descriptions matched, you can then go to the quiz, which you can do multiple times. Where's this quiz? Let's go back to materials. So you can do this quiz, which is right here. So name that motion check. If you go there, you can input all your... you can input your answers and check to see if it's right. Once again, this will show you how many are correct. It's not going to tell you which ones are wrong. So you'll have to flip it. And I've given you I think it's 17 or 15 or 17 tries that you can do. So there you go. Couple other things, couple other last minute things. One of them is the graphing motion, the name that motion handout is typically supposed to be done in a group. I prefer it to be done in a group, honestly. So if you want to get go to a Google Meets or Zoom or whatever it is you want to set up with your friends and work through it together, you are free to do that. However, your explanations and your motion dot diagrams that you make for that, those should all be your own. So yeah. But and a lot of this is often trial and error and getting the hang of this, because this is kind of there's a learning curve to this part. It's a new skill to have to think about how to translate position versus time graphs to velocity versus time graphs, and velocity versus time graphs to acceleration versus time graphs, etc., etc., etc. The last thing I want to talk about is the moving man. When you're doing the Name That Motion activity, I'll have a link to this, the moving man. So it's a PhET simulation, and you can go to it here. If you click on it, as long as you're using a computer of some sort, it can't be a cell phone, and it can't be like an iPad or something like that. Chromebooks, I think, will work. Chromebooks will work. So, but if you do this, you get this. It'll load up, I swear. So you get this activity. I would go already, I'm looking at the tabs. Instead of introduction, go to charts. And you can do things like change the position. So I'm moving the position. Let's see, I'll have the velocity of the man like this. I'm going to get rid of the walls. And I'll have the acceleration be like this. Sure. There we go. Oh, and then you also want to show the vector. Show the vector, yeah. And so you can see, play, and it'll show the graph as the man moves. That's a really bad graph. You guys can play with it probably better. So yeah, just kind of get a sense of play around with that, because that's something we're going to play around with on Friday as well. Let's see. There was one more thing I wanted to say. I forgot. Oh yeah. Acceleration is a vector. I didn't mention that. Acceleration is a vector quantity. So acceleration is a vector quantity. Vector. Very much so. So yeah, it's got direction. It can be pointing to the right, or it could be pointing to the left. So all right, that's it. Thank you guys. Bye.